Okay, so when we were doing LU decomposition, we had a matrix A which you could split into L and U without doing any row interchange. Okay, so that was what we referred to as direct factorization. Now, in a case where it's not possible to do that, because certain matrices, you can't just, when you try to do this LU decomposition, you might land in problems where one of the diagonal elements, especially the U11, U22, U3, one of those can end up being a 0. If it ends up being a 0, then factorization becomes impossible. Are we clear?
Yes, sir.
And we have mentioned this before to say if one of the diagonal elements becomes equals to 0, then you can do an interchange, or you can do what's referred to as pivoting. Now, there's a way of doing that interchange which involves use of a matrix, and this matrix which you're going to use, which does your interchange of rows, that is what is referred to as a permutation matrix. An example of a matrix like this, which does not actually do any permutation, is an identity matrix, which is a matrix where you've got ones along the diagonals and everything else is equals to 0. Such a matrix, when you multiply such a matrix, an identity matrix, with any other matrix, the resulting matrix is the same as what you multiplied with. Now, in the case of a permutation matrix is basically an identity matrix which has been rearranged. So basically, you rearrange the rows of your identity matrix, because in the first row for an identity matrix, the first item is 1. Then in the second row, the diagonal element is a 1. The third row, the diagonal element is a 1, like that. So in this case, you just interchange the rows of your identity matrix. Then what you end up getting is what's referred to as a permutation matrix. So when you have to use a permutation matrix so that it becomes possible for you to split a matrix A, this is what is referred to as indirect matrix factorization. So far, our assumption has that it's possible for you to split your matrix A into L and U. And if you can do that without any row interchange, that is what we have called a direct matrix factorization. However, it is not always possible to do this, for you to factorize your matrix into L and M like this. An example of a matrix where it's not possible for you to do factorization without doing a row interchange is one which we have here. So we will attempt to try to factorize this matrix A, which is 1, 2, 3, that's the first row, then 4, 8, minus 1, that is the second row, then minus 2, 3, 5, third row. We'll try to break this matrix into L and U so that we can show that it's actually certain matrices. You can't break them like this unless you have to do something else. So in that particular case, so what we are going to do, since we know that we can't break this matrix, and we are going to show how, we're going to work out things a bit differently, but the differently we're going to do is much faster than what we have been doing. It is also LU decomposition, except faster. So we write our matrix A, which is this one here. So this is our matrix A, and the whole point here is we want to break it into a lower triangular matrix, which looks like this, where you've got ones along the diagonals, then above the diagonals you've got zeros, then below the diagonals you've got the multipliers, M21, M31, M32, like this. Then this side you have your upper triangular matrix with U11, U12, U31, then here what is 0, then U22, U23, then 0, 0, then U33. For us to successfully do this, we have to make sure that all these guys, U11, U22, U33, all these guys are not equals to 0. If it's found out that one of these guys is equals to 0, then the whole process fails. Okay. So the way we're going to do this is, instead of doing the way we went, where we start doing Gauss elimination on this one, this bit, this A, this time around we're just going to leave it the way it is. What we're going to do is we're going to multiply this L times U. So we'll multiply L times U. If we multiply L times U, whatever we're going to get must be equal to A. Are we clear?
Yes.
So we're going to multiply these matrices. This 3 by 3 matrix multiplied by this 3 by 3 matrix, we're going to get a 3 by 3 matrix. And that 3 by 3 matrix, whatever we're going to get, when we equate it to this, they should be the same. So in this case, so the way we do it, we're going to multiply this first row, the 1, 0, 0, we'll multiply it by this first column. So first row multiplied by first column, it's going to give us what we're supposed to have here. That's what this number is showing you here. First row multiplied by first column here. So we multiply the first row times the first column. This first column here, U, 0, 0. Then next we multiply the first row times the second column here, U1, 2, U2, 2, U0. Then we multiply this first row times this third column here, U11, U13, U23, U22. So in all these cases, as you are multiplying this times that, what you're going to remain with, as you're going to see, is going to be your U1. We'll get to that. Then next, we'll multiply this second row times the first column, so that we can get what you're going to put here. Then we'll multiply the second row times the second column, so that we can get what we're going to put here. Then we'll multiply the second row times the third column, so that we can get what you're going to put in that particular position of this thing once we multiply it. Then third column, we multiply the third column times the third row times the first column, like that. So we'll get stuff here. We'll multiply the third row times the second column, we'll get stuff which is supposed to be here. We'll multiply the third row times the last column, we're going to get stuff which is supposed to be there. When we do that, this is what we end up with. So this is our A. And so this is us multiplying the first row multiplied by the first column. When you do that, so it's going to be 1 times this plus 0 times 0 plus 0 times that, which is going to give you this 1 times U11 plus 0 plus 0. And when you do this, you're going to get what you have here. Are we clear? You're going to get U11. Then we multiply the first row, us multiplying the first row times the second column. When you multiply first row times second column, you're going to have 1 times this, which is what you have here. 1 times U12, then 0 times U22, you're going to get a 0. Then 0 times 0, you're going to get a 0 here. So you end up with having 1 times U12 plus 0 plus 0, you're going to end up with U12, which is what you have down there. Are we clear on what you're doing? Here, we multiply the first row times the third column, which is that. So that's going to give us 1 times this plus 0 times this plus 0 times that, which is going to give you 1 times U13 plus 0, which is going to give you U13. Is that clear? Are you familiar with what you're doing? Multiplying. Yeah, so here I was saying we multiply row number 1 times with the first column. So that would be 1, 0, 0 multiplied by U11, then 0, 0. So this one here, it would be 1 times U11, that's what you have here, plus 0 times 0, that's what you have here, plus 0 times 0, that's what you have here. Then this bit here, when you add everything, you end up with U11, which is what you have here. Is that clear?
It's clear.
Then here, the first row multiplied by the second column, so that's going to be 1 times U12, that's what you have here, plus 0 times U22, you end up with a 0, plus 0 times 0, you end up with a 0. When you add all these, you end up with U12. Then here, that is the first row multiplied by the third column. So when you do multiplication of matrices, you multiply the rows of the matrix in front by the columns of the second matrix. So in this case, the first row multiplied by the third column. So that's going to be here. You've got your 1 times U13 plus, that's what you have here. Then plus 0 times U23, that's what you have here. You get a 0. Then plus 0 times U33, that's what you have here. So when you add your 1 times U13 plus 0, you end up with U13. Then we move on to the second row. We multiply the second row of the lower triangular matrix by the first column of the upper triangular matrix. So that's going to give us M21 multiplied by U11. That's what you have here. M21 multiplied by U11, then plus 1 multiplied by 0. You're going to get a 0. Then plus 0 multiplied by 0. You're going to get a 0. So you end up, when you add all these, M21 plus multiplied by U11 plus 0 plus 0, you're going to end up with M21 U1 here. Then this bit here, the second row multiplied by the second column, the second row of the lower triangular matrix L multiplied by the second column of the upper triangular matrix U. So that's going to give you M21 multiplied by U12. That's what you have here. M21 multiplied by U12, then plus 1 multiplied by U22. 1 multiplied by U22, that's what you have here, plus 0 multiplied by 0, that's what you get here. So you end up having M21 multiplied by U12 plus 1 times this. You end up having M21 times U12 plus U22, which is what you have here. Okay, then you multiply your second row multiplied by the third column. So that's, this one is going to give, you're going to have M21 multiplied by U13. So here M21 multiplied by U13, then plus 1 multiplied by U23. Here 1 multiplied by U23 plus 0 multiplied by U33, which is going to give you a 0 here. So when you add all these, M21 times U13, then plus 1 times U23, you're going to end up with this M21 times U13 plus U23. That's what you're going to end up with there. Is that clear?
That's clear.
Okay. Next, the third row of the lower triangular matrix, which is M31 U23 multiplied by 1 multiplied by the first column of the upper triangular matrix U1 0 0. So you're going to end up with your M31 multiplied by U11. You're going to, in this one, M31 multiplied by U11 plus your M32 multiplied by 0. You're going to get a 0. Then plus 1 multiplied by 0. You're going to get a 0. So at the end of the day, when you add up this, you're going to end up with M31 plus U11 plus 0 plus 0. So you're going to remain with only M31 times U11. Is that clear? Then here, the third row of your lower triangular matrix multiplied by the second column of your upper triangular matrix. So that's going to be M31 multiplied by U21. That's what you have here. M31 multiplied by U21 plus M32 multiplied by U22. So you have M32 multiplied by U22 plus 1 multiplied by 0. You're going to get a 0. So when you add all these things, you're going to end up with M31 multiplied by U12 plus M32 multiplied by U22. That's what you have here. Next, your third row multiplied by third column. So this is going to give you M31 multiplied by U13. M31 multiplied by U13, that's what you have here. Then plus M32 multiplied by U23. That's what you have here. M32 multiplied by U23 plus 1 multiplied by U33. That's what you have here. So when you do this addition here, so you end up with M31 U13 plus M32 U23 plus U33, like this. So what we have on the left hand side is our matrix A. What you have on the right hand side is a product of the lower triangular matrix and the upper triangular matrix, which is this. So these are the same if we assume things have been done correctly. Are we clear?
Yes.
So in this particular case, if these things are the same, if they're equal, then it means that this one here, which is A11, should also be equal to this one here. Are we clear?
Yes.
Then this one here should be equal to this one. This value here should be equals to this. This value here should be equals to this expression here. This value here should be equals to this expression here. This value here should be equals to this expression here. Then this value here should be equals to this expression here. Then this value here should be equals to this expression here. Then this one should be equals to what you have here. If we go along that road, then you notice that your 1, which is what you have here, is going to be equals to U11, which is what you have here. 1 is equals to U11, therefore your U11 is going to be equals to 1, which is the first element in your upper triangular matrix. So U11 is going to be equals to 1. Are we clear?
Yes.
Then if you come here you've got a value of 2, so this is supposed to be equals to this one. So this bit here, this value 2 is supposed to be equals to this U22. So your U22, your U12 is going to be equals to 2. So your U12 is going to be equals to 2, and this is what you get here, U12 being equals to 2. Okay, then you move on to this one here, the 6. This 6 value is going to be equals to this one here, U13. So when you do that, you end up with following. So you end up with 6 being equals to U13, and therefore your U13 is going to be equals to 6. Okay. Then the other bit will be this one, the 4. The 4 is going to be equals to this, M21 U11. So 4 is going to be equals to M21 multiplied by U11. We already have the value for U11. U11 is equals to 1. So when you do that, so when you say the 4 is equals to here, 824, 824 is equals to this plus times that. So here 4 is going to be equals to M21 multiplied by 1. That's going to give you 4 being equals to M21 and M21 being equals to 4. Are we clear? This value of U11 we have already found up here. Here. Is it clear?
Yes.
Okay. Then we move on to this bit here. 8. This 8 value is supposed to be equals to this. M21 multiplied by U12, then plus U22. M21 we have just found, U12 we found earlier. So M21 we just found, U12 we have found. U12 is this one, U12 is 2, and M21 we have just found is M21 we just found out before, which is what we found up here, 4. So when you do that, we end up with 8 equals to M21, which is 4, times this one, which is 2, plus U22, and 8 this side. This times that is going to give you 8. So 8, you got 8 this side, you got 8 this side, then plus this bit. So you take one of the 8 outside, so you end up with U22 equals to 8 minus 8, end up with U22 being equals to 0. So you see the diagonal element in the upper triangular matrix, this U22 is equals to 0. This guy, U22 is equals to 0. If U22 is equals to 0, then it simply means that the determinant of our matrix A is equals to 0, because for us to work out the determinant, remember what you have to do? We need to multiply. We need to multiply U11 times U22 times U33. So if you multiply this and the determinant is not equals to 0, then it simply means that there's a solution to this matrix. So in this case, one of the diagonal elements U22 is equals to 0. That simply tells you that there is no solution the way this matrix is, if you do it without an interchange. So in this case, U22 is equals to 0. Then next, if you continue in this particular process, you come to this one. After finding out that U22 is equals to 0, you continue this process, we come to this bit here. This one, minus 1. So it's minus 1 equals to M21 multiplied by U13 plus U23. So when you do that, you end up with the following. You find it. So that's going to be minus 1 equals to 4 times M21 is 4, then U13 is 6 plus U23. That's what you're looking for. So you substitute here, there. You're going to end up with 4 times this, 24, then plus U23. Then you get this guy to the other side, so you're going to end up with U23 being equals to minus 25. That's okay. Okay. Then if you move on to this other bit here, you minus 2 here, you've got a minus 2 here. With this minus 2 expression is equal to this. That's going to be M31 multiplied by U11, and the value for U11, we know U11 is equals to 1. So that's going to be, when you do that, so we're going to end up with M31 which is equals to minus 2 equals to M31 times U11, but U11 we know is equals to 1, so it's going to be minus 2 times M31 times 1. That's going to be minus 2 equals to M31. So M31 is going to be equals to minus 2. No problem, that's fine. Then we move on to this guy here. We move on to this guy here, 3. So 3 is going to be equals to M31 multiplied by U12 plus M32 multiplied by U22. This bit here, this U22 we have found is equals to 0. So when you do that, so you end up with 3 equals to what we have here, like that. So you notice what will happen. We will fail to find what is supposed to be the value for the other one. So the A32. So for A32, so that's going to be 3 here equals to M31 multiplied by U12 plus M32 multiplied by that. So you put in the values for this and that. That's minus 2 here, 2 plus M32 multiplied by this guy, which is equals to 0 this side. So when you do that, you end up having 3 equals to whatever this is. This is minus 4, then plus M32, 0. Then you see there's already a problem here. If you take this side to this side, you end up with 7 is equals to M32 times 0. If you try to work out your M32, you end up having M32 is equals to 7 divided by 0. You see this?
Yes.
So that's where the problem starts. This problem is starting because it's showing up because this guy, U22, which is a diagonal element, is equals to 0. So with the way things are, it's not possible for you to proceed with your factorization because you don't know what the value of M32 is. You can't find the value for M32. Are we clear?
Yes.
So the lesson here is that there are actually certain matrices you can't factorize into a lower triangular and an upper triangular matrix as long as you're not doing any row interchange. Okay, is that clear?
Yes.
Okay. Now, how do we solve this problem? The way we solve this problem is by doing a row interchange. And how do we do a row interchange? We use a special matrix called a permutation matrix. This permutation matrix is usually a square matrix. It's an n by n matrix. And in this permutation matrix, things are arranged in such a way that in each column, there's only, each row has only, all the other elements in that particular row are 0 except for 1, which is equals to one element which is equals to 1. So for a permutation matrix, each row and column only have 1, 1. For example, I'll need to show, for example, here, if you look at the first column here in this permutation matrix, this is an example of a permutation matrix, a 4 by 4 matrix. If you look at the first column in this permutation matrix, there's only one value. There's only one row here in this first column. For all the other rows, you've got zeros except for this one here. The same thing, if you come in this column here, second column, there's only a 1 here and everything else is a 0. In this column also here, there's only a 1 here and everything else is a 0. In this column also here, there's only a 1 here, everything else is 0. If you look at it in terms of rows, you see that in the first row, there's only a 1 here and everything else is 0. In the second row, you see that there's a 1 here and everything else is a 0. In the third row, there's only a 1 here and everything else is a 0. In the fourth row, there's only a 1 here and everything else is 0. This kind of a matrix is called a permutation matrix. How was this matrix formed? It was formed by rearranging an identity matrix, because the identity matrix this one was used to, which was used to make this permutation matrix, had this one, this second row as the first row. So if you make this one your first row, so you bring it here, so you're going to end up with 1 0 0 0. Then this first row, you make it your second row, you're going to end up with 0 1 0 0. Then this last row here, you bring it here, you're going to end up with 0 0 1 0. Then this last row, you put it here, you're going to end up with 0 0 0 1. Are we clear?
Yes.
So the way you form a permutation matrix is you interchange the rows of the identity matrix. You start with an identity matrix, which has got a 1 here and everything else 0. Then it has got a 0 here and everything else 1 here. So in an identity matrix, only the elements along the diagonal have got 1s. Everything else is equals to 0. Are we clear? Only diagonal elements have got values of 1, and everything else which is not a diagonal element, any other element which is not a diagonal element, has got its value set to 0. So it is this matrix, this identity matrix, whose columns you rearrange to obtain your permutation matrix. Are we clear?
Yes.
So there are only so many permutation matrices you can get from a particular identity matrix. Okay? Basically, we are asking you how many ways can you rearrange an identity matrix? There are only so many ways you can do that. So those matrices you obtain by rearranging an identity matrix, that is what is referred to as a permutation matrix. Now, what you might not be aware of is, what does this matrix actually do? If you've got a matrix like this, what is it going to do to your matrix A? So what you're going to do next is you're going to multiply our permutation matrix, this one, we multiply it by the matrix A. When you do that, you're going to get a new matrix, a 4 by 4 matrix. But in this new matrix, you will notice that the order of the rows has been rearranged. So here we have got our permutation matrix. This one is our permutation matrix. This is our matrix A. So we've got A11, A12, A13, A14. Then you've got A21, A22, A23, A24. Then you've got A31, A32, A33, A34. Then A41, A42, A43, A44. If we multiply this matrix P times matrix A, so we're going to have the following: PA, that's going to be this permutation matrix, then multiplied by matrix A. When we do that, we're going to do the following. We're going to get the following: For the first, so we're doing matrix multiplication. This first row multiplied by the first column. That's what you're going to put here. When you do that, everything else apart from this is going to multiply this here. So you end up with this here. Then first row again multiplied by second column. So everything, this will be multiplied by 0, this will be multiplied by 1, this will be multiplied by 0, this will be multiplied by 0, so you end up only having this guy. So you put it there. Then this first row multiplied by third column. So this one will be multiplied by 0, this one will be multiplied by 0, this one will be multiplied by this times this. Yes, so this one will be multiplied by 0, this one will be multiplied by 1, this one will be multiplied by 0, this one will be multiplied by 0, so you end up with 823. Then this one multiplied by this guy, so this first one will be multiplied by 0, this one will be multiplied by 1, this one will be multiplied by 0, so you end up with things. So what you notice here is the following. If you look at what you have here, is what you notice you've done is that you have moved what was your second row, it's now your first column. Your first row. What was the second row in A? In your permutation, in your P times A, it now becomes the first column. Are we clear?
Yes.
When you do here, row number 2 multiplied by this, so it will be 1 multiplied by this guy, then everything else multiplied by 0. So you're going to end up with A11 here. This one, row number 2 multiplied by this, it will be second row, second column. So it's going to be 1 times this, then everything else below here multiplied by 0. So you're going to end up with A12. Then this one here, second row multiplied by third column, it will be 1 times this, then everything else below multiplied by 0. So you're going to end up with A13. Then this times this. So you're going to have 1 times A14, then everything else multiplied by 0. So you're going to end up with this here. So you can see with this row 0, 1, 0, 0, you have moved your second row. It's now the first row. Then with this one, you have moved your first row. What was your first row is now your second row here. With this one, you can guess what was the fourth row will now become the third column. And that's exactly what happens. If you do this multiplication, this times this whole thing, so everything, all the first three, this will be multiplied by 0, multiplied by 0, multiplied by 0, this will be multiplied by 1, so it becomes F01 here. Then this times this thing here, so this guy will be multiplied by 0, multiplied by 0, multiplied by 0, multiplied by 1, so you're going to end up with F02. This whole thing here multiplied by this, so this guy is multiplied by 0, this is multiplied by 0, this is multiplied by 0, then this one you end up with F03. Then this whole thing here multiplied by this, so you're going to end up having this guy being multiplied by 0, multiplied by 0, multiplied by 0, then multiplied by F04, so you end up with this. So you can see you have your A4, F41, F42, F43, F44 as your third row. Then we come to this one here. So this one, what is going to happen here is that whatever was the third row is now going to become the first column. So whatever was the third row is now going to become the fourth row. So this one 0, 0, 1, 0, you multiply by this, so you end, this guy is multiplied by 0, this is multiplied by 0, this is multiplied by 1, this is multiplied by 0, so you end up with A31. Then this whole lot here multiplied by this, you're going to end up having this is being multiplied by 0, multiplied by 0 here, this is multiplied by 1, this is multiplied by 0, you end up with A32. This bit here multiplied by this, so you have A31 multiplied by 0, A32 multiplied by 0, this one multiplied by 1, this one multiplied by 0, you end up with A33. Then this whole lot here multiplied by this, so you have this, multiplied by 0, multiplied by 0, multiplied by 1, multiplied by 0, you end up with this. So you can see what your permutation matrix does. Your permutation matrix, when you have a permutation matrix, P, you multiply your permutation matrix by A, what it simply does is that it rearranges the rows of matrix A. Are we clear?
Yes.
Your permutation matrix P is going to rearrange the rows of matrix A. Your permutation matrix is not easy to, it's not difficult to find. You simply start with an identity matrix, then you rearrange your things. Okay? Because if you multiply with an identity matrix is a special type of permutation matrix, in that it does not change anything. The rows, if you multiply I times A, you still get A. You still get the same A with all the rows the same way as they were before. But if you play with the rows of the identity matrix, if you move one row, you interchange the rows of the identity matrix, then what you end up getting is a permutation matrix, and that permutation matrix will result in you doing an interchange of rows. Are we clear?
Yes.
Okay. So here's the thing. If you've got a matrix A, okay, then you can't do direct factorization in this particular matrix A. There will be a matrix you can find from the size of A. There's a matrix you can find, properly find. There's a proper matrix you can find where you can multiply this matrix A times matrix P times A, so that you get this. When you do that, you multiply P times A, then it becomes possible for you to do this, L times U. Are we clear? It becomes possible for you to do the L times U. Now I created some. I don't think it's a good permutation matrix, but it shows what we are trying to put across. This is the same matrix we were this is the same matrix we were trying to break, and we couldn't because there was a U22 being equals to 0. Okay, so if I multiply this same matrix with a permutation matrix of, for example, this particular fashion here, where it's not a good permutation matrix, but it shows what kind of power these things have. Where the first row, I just leave the first row the way it is. So I don't want to change the first row. The only thing I want to do is I want to change the second row and the third row of this matrix A. I want to leave the first row the way it is. So I just leave, because you need to start with when you're creating a permutation matrix, you start with an identity matrix. 1, 0, 0. Then this is supposed to be 0, 1, 0, then 0, 0, 1. So what I do is I interchange this one, which is supposed to be 0, 1, 0, and this one 0, 0, 0, 0, 0, 1. I interchange this second row and third row of the identity matrix. Then I obtain this permutation matrix. Are we clear?
Yes.
Is it a good permutation matrix? From what I've done here, it's not a very good one, but it allows us to do factorization. So with this permutation matrix, so what we do next is we multiply P times A. So the permutation matrix, this one, times the matrix A, when you do that, so 1, 0, 0 times this guy here, this first column, I get a 1. So 1 times 1, 1, 0 times 4, 0, 0 times 2, 0, so I get a 1 here. So there's no change in the first row. This first row multiplied by the second column, so it will be 1 times 2, 0 times 8, 0 times 3, so I get a 2 here. Then 1, 0, 0 times the third column, So 1 times 6, 0 times 5, 0 times minus 1, so I get a 6 here. So 1 times 6, then plus 0 times minus 1 plus 0 times 5, so I get a 6 plus 0 plus 0, I get a 6. So you can see my first row is the same. My first row has not been changed. Okay, then I do the following here. Now second row of the permutation 0, 0, 1 times the first column. Yeah, here. So this is going to be 0 times 1 plus 0 times 4 plus 1 times minus 2. Then I get my 2, which is here. Then this one, second row times second column. So it's going to be 0 times 2, 0 plus 0 times 8, 0 plus 1 times 3. I get my 3 there. Then here, third row multiplied by second row multiplied by third column. So that's going to be 0 times 6, 0 plus 0 times minus 1, 0 plus 1 times 5. I get my 5, which is what I have here. Then this last one here, 0, 1, 0. So 0 times first column. So 0 times 0 is 0 plus 1 times 4 is 4 plus 0 times minus 2 is 0. So I end up with a 4 here. Then last row times second column. So 0 times 2, 0. 1 times 8, 8 plus 0 times 3, 0. So I end up with my 8, which is here. Then here, third row multiplied by third column. So that's going to be 0 times 6. I get a 0. 1 times minus 1. I get a minus 1. 0 times 5. I get a 5. Then I get these. So basically, this is the result of me multiplying P times A. With this, my first row is unchanged, but the second and third row have been changed. Then after finding my PA, so this is my PA. This is my PA. Now with this PA, if you multiply P, which is a permutation matrix, times A, it becomes possible for you to do ALU decomposition. And we're going to do it the same way we did it earlier. We tried to do it earlier. So where this PA, we can factor this PA into a lower triangular matrix, which is going to be, it's going to have ones along the diagonal. Then above, we're going to have zeros, then M21, then M31, M32, down here. Then up here, we're going to have U11, U2, U12, U23, then 0, U22, U23, 0, 0, and stuff like this, U33. Okay, so if we are going to have a good factorization, in this case, because of the kind of thing we have, we don't have a good factorization. But if we are going to have a good factorization, all these guys below M2, M21, M31, M32, these are not supposed to be equal to zeros. But in our case, because we are not using a good permutation matrix, one of them is equal to 0, but our upper triangular matrix comes out just fine. So when we multiply this row, the first row, times this column, first column, you end up with U11. We have seen how to do this. We multiply first row times second column, we end up with U12. We multiply first row times third column, you end up with U13. You multiply second row times first column, you end up with M21, U11. You multiply first row, second row times second column, you end up with M21, U12 plus U22. Then second row multiplied by third column, you end up with M21, U13 plus U23. Then we multiply third row times first column, you end up with M31, U11. Then this bit, third row multiplied by second column, you end up with what you have here. Then third row multiplied by last column, you end up with what you have here. What we are trying to show here is as long as P is a permutation matrix, okay, you multiply P times A, it will become possible for you to do factorization. The question is the quality of the factorization. How good is your permutation matrix? So if you've got a good permutation matrix, then things become easier. Okay, so from what we have, you can see that your 1 here is going to be equals to U11. So U11 is going to be equals to 1 there, right? U12 is going to be equals to 2. That's what you have here. Then U13 is going to be equals to 6, which is what you have here. Then this bit here, M21 U11, M21 U11 is going to be equals to minus 2. So M21 U11 is going to be equals to minus 2. So you end up with M21 U11 plus where is, have I missed something? Or why did I start with this one? I think I missed something. So this one, this is close to, because I was supposed to do this. M21 U11 is equals to minus 2. U11 is 1, therefore M21 is going to be minus 2. And I have it here, but I don't know where did I work it out. Yeah, I think I missed something, but that's fine. Okay, then we move. Okay, so M21 is minus 2, U12 is this, plus U22 equals to 3, so this times that is minus 4, plus U22 equals to 3. I get this guy to the other side, so I end up having U22 now being equals to 7. Previously our U22 was equals to 0, if you recall.
Yes.
Okay, so now it's equals to 7. Then you move on to this other guy. This one here, I don't know why things are this one here, so this one should be equals to this.
We're supposed to find the U23 now.
Yes, U23. So for U23,
Yes.
that's what you have here. M21 multiplied by U13 plus U23 equals to 5. Then M21 is this, U13 is 6 plus this much equals to 5. This times that is, it gives you minus 12 plus U23 equals to 5. Then U23 is going equals to 17, and so your U23 is now equals to 17. Okay, then we move on to the last row, which is this one here. So this one you've got a 4, you got M31 U11 equals to 4. U11 we know is 1. So when you do that, you end up with the following. Yeah, here M31 U11 is equals to 4, U11 is 1, so you end up with M31 being equals to 4. Okay, then next you have this bit here, M31 U12 plus M32 U22 equals to 8. So when you do that, you end up with what you have here, M31 U12 plus M32 U22 equals to 8. So you end up with 4 times 2, 8 plus M32, then U22 is 7, and that, so here you end up with 8 plus 7 M32 equals to 8. This side, you take this to the other side, you end up with 7 M32 equals to 8 minus 8. Then you end up with 7 M32 equals to 0. Then M32 is going to be equals to 0 divided by 7. You end up with M32 being equals to 0. Now this is as much as we can proceed and reach the end. You see, the rule about forming so this is what you have here is a permutation matrix which is not good. Because the rules about your lower triangular matrix is that everything below the diagonal is not supposed to be, anything below the diagonal, below the ones, is not supposed to be equal to 0. But here we have something which is equal to 0. You see that?
Yes.
So this is showing you that the permutation matrix we have, as much as it is a permutation matrix, it's not a good permutation matrix. Okay? But
Yes.
but it shows something to say when you multiply your P times A, it becomes possible for you to get you something which looks like L times to do factorization of L multiplied by U. Then if you move on to the last bit, this one here, so minus 1 multiplied by this here, like that. So this 1 equals to this M31 U13 plus M32 U22 plus U23 is equals to minus 1. Then if you do that, then you end up with the following. You end up with this equals to minus 1. You put in the values for all these, so you end up with 4 times 6, which is 24. Then this bit is 0 here. This times 7 is 0. Then plus U33 equals to minus that. You end up with 24 plus U33 equals to minus that. Then U33 equals to minus that. You end up with U33 equals to minus 25. So with this, then it's possible for you to write your factorization L times U. So you end up with PA, which is this, your PA, which is this. Then this is going to give you this as a lower triangular matrix. But the problem is this here, and you end up with your upper triangular matrix this side. Your upper triangular matrix is fine, but the problem is this here. So the quality of so our permutation matrix, which we have chosen to use in this particular case, is not a very good one. But what it shows is that if you get your identity matrix, then you rearrange it, then you play around with it. It's possible for you to come up with a matrix PA which you can properly break down into L and U. Are we clear?
Yes.
So that is what you do when you are trying to. This is a step this is an additional step you do when you are trying to do when you're trying to factorize your matrix A. But it's not possible for you to break it into L and U directly. So you look for a matrix P, which is a permutation of the identity matrix. So you pick one of the permutations, the identity matrix permutations, one of them, then you multiply it with A, then you see where it goes. Usually you will be given a permutation matrix, a proper one. So if you have to go this way, we give you a proper permutation matrix, we give you A, then we tell you do the factorization, then find whatever things you have to find. Are we clear? Is it clear? So this brings to a close our chapter 2, where we are talking about systems of linear equations. So chapter 2 has come to an end, which represents 40% of the exam. Then we will in the coming weeks, this week, Wednesday, when you meet on Wednesday, hopefully we can meet on Wednesday, Saturday, Sunday, we want to do another topic called polynomial approximation and interpolation. Hopefully it can be finished. If it can be finished, that's fine. Then that other week, over the weekends, we look at something called K-fitting. Then that other week, we look at something called numerical differentiation. Then that other week stuff, we can look at integration. Then after that, I think that's enough for your exam and for your tests. So we can get rid of your assignments, your exam, your your 2 tests. So the only thing that's going to be left will be your labs.
Okay.
Yeah. The assignment which you received last week is due on Tuesday. So by Tuesday, Wednesday, you will receive another assignment concerning what we have been looking at, which is going to be due next week. And that's how we are going to operate until we close up this chapter. Okay, so if you've got any questions, you can ask, but otherwise, hopefully you can meet on Wednesday.
Yeah, I'll meet on Wednesday. Except today, I just broke my arm.
You
So
broke
I'm in POP.
You broke your arm. How?
Yeah, I slipped on the stairs.
Oh, sorry to hear that.
So my right arm is broken, both the bones around the wrist.
Oh, that's very bad. Okay.
I'll meet on Wednesday. Otherwise, I'm really understanding these things.
Okay, that's very good. Thank you very much. See you on Wednesday.
Okay, see you. Thanks.